Welcome back, and this is the second in the series of videos looking at the alkenes. In this video we're going to be looking at the EZ naming system, and we're going to be going on to look at some of the reactions of the alkenes. So you're going to need your notes, and we're starting on page 5. So most situations we'll be using the EZ naming system rather than the cis-trans version. So the way we can work out which version we've got, E or Z, is by looking at the atoms bonded to the carbon double bonded carbon. So we're looking for the atom with the highest atomic number. That's what takes priority. If you've got two atoms with the same atomic number, then you look at the next atom along, and so on. If obviously you get to the end of the molecule and there are no differences, it won't show geometric isomerism, because two of the groups on a carbon of the double bond will be the same. So if we look at an example, the order of priority amongst bromine, carbon in CH3, chlorine and hydrogen. Well, of those four, bromine has the highest atomic number, so it has the highest priority. Then chlorine, then the carbon in the CH3 group, and then last but not least, hydrogen. Hydrogen always has the lowest priority because hydrogen has atomic number 1. So next group, if we look at these, and we can see the little line represents where that fragment is bonded onto the carbon of the double bond. So looking across these four, this is the one with the highest priority because the first atom bonded to the carbon double bond is an oxygen, and that has a higher priority than any of the others. So the first one is CH3O. Now we've got a bit of a problem in that we've got a carbon, and a carbon. So we're going to look along one more along the chain, and we have an oxygen, a carbon and a hydrogen. So obviously the oxygen has the highest priority, so that one comes next. Then the carbon, so it's a CH3 CH2 group, and then last but not least it's the CH3 group. So putting in the little arrows to show where it is bonded on. So if we look at this example, looking at these two groups on the first carbon of the double bond, this group has priority because it has a higher atomic number than hydrogen. Then choosing between these two, well, bromine has a higher atomic number than carbon, so bromine is the highest priority. In this case, the two groups with the highest priority are on the same side, therefore we call this Z. So this is the Z version. So if the two groups with the highest priority are on the same side, it's the German for zusammen, it means together, they have a designation of Z. If the two groups are on opposite sides, that would be the E version. So the molecule we just looked at, 1-chloro, 2-bromo-propene, was the Z version. So I put the Z in front of the name to tell me I've got the Z isomer. A few more examples for you. Again, here I have the two highest priority on the same side. Get the Z version. Here they are on opposite sides. Again, in this case, my chloro is the highest priority because it's higher priority over carbon, and obviously the carbon has the higher priority over the hydrogen. So this is again the Z version, and here we have the chloro and the carbon on opposite sides, therefore we've got the E version. Moving on to page 6 of your notes, we're starting to look at some of the reactions. Now, one of the first reactions you need to know is the reduction or addition reaction of hydrogen. It can be classified as both a reduction reaction because you've got a gain of electrons, but it can also be classified as an addition reaction because you're adding across the double bond. So if we think about the old-fashioned view of reduction, as the gain of hydrogens. So in this case you're going from 4 hydrogens to 6. It also means you're actually gaining electrons. And we're going to study reduction and oxidation reactions in more detail when we study redox. So this is not an easy reaction to do. It requires either a nickel catalyst at 150 degrees Celsius or a platinum palladium catalyst at room temperature. However, it's very useful. This would be called an unsaturated. This is a saturated molecule, and that's very useful for food manufacturing in the production of things like margarine, where we can take unsaturated oils and turn them into saturated fats which have a slightly higher melting point, and therefore you can turn an oil into a spreadable margarine. So you need to know this reaction. You need to be able to classify it as reduction or addition, and you need to be able to give the catalyst and the degree to which it needs to be heated for this reaction to work. And you also need to know why it's useful. The addition reaction doesn't come up very commonly with hydrogen. However, there is a group of reactions called the electrophilic addition reactions of alkenes, which come up frequently and you need to know in a great deal of detail. So alkenes often undergo addition reaction. This is where we're going to add a molecule to my unsaturated alkene to turn it into a saturated product. So you need to know these definitions, where one or more groups are added to a molecule and it gives a single product. So it's got usually a very high atom economy. In fact, in this case, without doing any calculations, I can show that it's 100% atom economy. So it's a very efficient way of making our products. So alkenes generally undergo these addition reactions. This links back to something we looked at in the first video. Our pi bond is considerably weaker than the sigma bond, so it's quite easy to break that bond, and when it breaks, 2 atoms can be added, 1 to each carbon of the double bond. Now the type of reagent which is most likely to be attracted to the double bond is what we call an electrophile. Electro and then phile. It means electron loving. Now the definition of an electrophile is an electron deficient species with a vacant orbital, and that's the important part of our definition. They are often, but not always, positively charged, and they react by accepting a pair of electrons by forming a new covalent bond. But it's this vacant orbital which defines an electrophile. Examples of this are anything really with a positive charge on it or with a delta positive charge on it. Delta means a small bit, and we often show that using this sign. That means a delta. It doesn't mean it's got a full positive charge on it, it means it's got a slight negative charge. So for example, HBr, the Br would be slightly negative and the H would be slightly positive. The reason for that is bromine is a more electronegative than the hydrogen. Now electronegativity is something we're going to be studying later on, but for the moment you need to think about the bromine being better able to pull electrons towards it, so it takes more than its fair share of the electrons in that covalent bond. So that is an electrophile. In this case it's the hydrogen end which is acting as the electrophile. There are other ones you're going to come across later on. So for example, NO2 positive, that's another very strong electrophile. This time it has a full positive charge. But in the case of the alkenes, we only really need a delta positive. In the alkane pact, we looked at homolytic bond fission, where we broke up something to form 2 of the same species. In this case, we're going to be doing heterolytic bond fission, breaking the bond to form 2 different ions. So we can break a bond between A and B, where A becomes negative and B becomes positive, or we can break it up so A becomes positive and B becomes negative. So for example, we have hydrogen chloride here, which can be split up into hydrogen positive ion and a chloride negative ion. Because the chlorine, like the bromine, is more electronegative than the hydrogen, it generally speaking gets the negative charge. So let's look at the first example of this, ethene with hydrogen bromide. So the reagents are simply my hydrogen bromide, which is the gas, and the conditions I can do this at room temperature. So if we look at the equation using displayed formula, I have my ethene molecule with the carbon-carbon double bond. Remember, that's 1 sigma and 1 pi bond. And I have my hydrogen bromide, HBr. This will add across the double bond, so I get an extra hydrogen on one of the carbons and an extra bromine on the other carbon. I've gone from an unsaturated to a saturated, and my product name is bromoethane. Notice I've now gone to an ane because I've lost the double bond, and I've added a bromo group, so I've made a halogenoalkane. And this is quite an efficient way of making a halogenoalkane because there's only one product, so the atom economy is 100%. It's far more efficient than doing the free radical substitution mechanism we looked at in the previous topic. So that's it for this video for today. In the next video, we're going to be going on and looking in more detail at this mechanism. It's one of the mechanisms that you need to learn in the lower sixth, along with the free radical substitution mechanism we looked at in the alkanes pack. So until then, take care, stay safe, bye bye.